Hello everyone, welcome back to this channel. Today we are going to cover the third video on this series of decision trees. So in the first presentation, we saw that how decision trees, what a decision tree is and how they are created. And we understood the basics in the first presentation. In the second presentation, we saw that what measures or metrics are used to decide what split and how the branches will be created and how the leaf nodes are created in the best possible way. We understood the metrics in the second part. Now the third part will cover another aspect of decision trees, where in real life we will have data which will have both qualitative and quantitative data. So there would be columns in a database. There would be aspects where some of the variables will be purely categorical. It will have one, two, or three category of values, and it could be a continuous data. It could have a numerical value. So CART algorithm takes care by handling both these two dimensions in a single algorithm. And this is what we So what we will cover in this presentation is handling both numerical and categorical data in a single algorithm. And the prerequisites to this presentation or this video is the basic understanding of a structure of a decision tree and how the nodes are created, understanding of Gini index, entropy, and information gain, which we covered in the second presentation. So, introduction to CART algorithm. As I just said, that it will handle both classification for categorical data and regression tasks for continuous or numeric data. CART serves as a generic term for classification and regression. And the key concepts in this algorithm are this is a quick brush up of what we covered in the previous two presentations. What is a root node? The topmost node that presents the entire data set. The decision nodes where splitting happens, and the leaf nodes which have the most homogeneous or one category of data. These are the terminal nodes where a tree, the flow of a tree ends at the leaf nodes. And these are the splitting criteria. We have already covered gene impurity and information gain. Today we are going to cover variance reduction. So we saw how partitioning of data happens. So we are creating branches using a partitioning criterion, and that criterion was identified using the Gini index or the information gain. So we understood those metrics in the previous presentation. So today we are going to understand the same thing with a different perspective. This is just a couple of slides added just to get a deeper and a better understanding of decision trees. So an understanding which would help us not to forget how the splitting happens basically. So whenever we have a one-dimensional data would have a single dimension of values, and this is a two-dimensional space, and this is a three-dimensional space. So what I'm trying to say through this image is that a three-dimensional space would have three axes X, Y, Z, right? So any data could be defined using three dimensions. So it could have three dimensions. So let me be a point of data. I have age, I have gender, and I have one more numeric data to define to cover me in a data set. So my presence in a database is defined by three aspects, that is X, Y, Z. So age is numeric, it is continuous data. Then gender, male, is categorical, which could be another dimension, and Z could be another dimension, whether I default on a loan or not. So that could be one dimension to understand, and that could be the target variable as well. So male and age, in a vague example, if you're trying to understand that a male with a certain age is likely to default on a loan or not. So this is a very extreme example. We'll have a lot of number of variables, but this is just a basic way to understand what I'm trying to make. My point here is that these are the three dimensions. So any data point in a database could have a large number of dimensions instead of these three. So a human can perceive a data point through three dimensions. Just imagine an n-dimensional space wherein n minus one dimensions are there, and there is one target dimension that we need to know. So from existing data from this point, so say this point is there, has certain value of x and y and z to identify its location. So this is what we know. We know x, y, and z. Now we have another data point in this where we will have x and y, but we don't know the z. And we using this existing points, this existing knowledge, we are trying to predict that z part of that new data point. This is what machine learning essentially does. This is what we are targeting, and this is what even decision tree will do. So now let this be an input space, and this could be a two-dimensional space also for the sake of understanding. So what we'll do is we will partition the input space, and then the measures for an effective split using information gain Gini coefficient, Gini index, what we did in the previous presentation. These measures are used after uh, to split the space into regions. So let this be a two-dimensional space, input space, and these be the regions, one, two, three, four, 5 regions. And these regions are created by points T2 and T4 on X, and T1 and T3 on X2, and T1 and T3 on X1. So X1 and X2 are the two dimensions. T2 and T4 are two values which we know in this X2 dimension, and T1 and T3 are two values which we know in X1 dimension. And these T2, T4, T1, and T3 are creating regions in this two-dimensional space. Similarly, in an n-dimensional space, different regions will be created using known values. So how a decision tree will work is, let x1 and x2 be dimensions of a two-dimensional space right here. One of these two variables could be a target variable. So I know x2, I need to know x1. Let that x1 be a target variable. Existing knowledge of x1 and x2, independent and target variables, will help us make predictions on new data points. So we have n number of data points within this input space, and we know that this space is divided into regions using these points T1, T2, T3, and T4. Now, having knowledge of T1, T2, and T3 and T4, and if we have a value of x2, if we have a certain value of x2 dimension, we can machine learning what this algorithm will try to pinpoint that point in this input space. This is what we're trying to do. Just stay with me. This will get clear in the next part, in the next slide also. So from the known values, series of decisions are identified, which will help us allocate these points into regions or subspaces. So by decisions, we mean that these values T2, T4, T1, and T3 are creating regions. So the decision would be how these regions will be defined. So if this region is R1, how this R1 will get to be defined? How this T2, how we will get this T2? This T2 will decide that this area belongs to R1, right? T2 and T1 combined are, giving this. So this is what the entire this entire exercise intends to do. So from knowledge of independent variable and new data, if we have new data and we have this space and we have this independent variables. So we said that let x2 be the independent variable and x1 be the target. So we have knowledge of x2 in that input space, and we need to know x1. So if we can answer these questions, whether that it's like a quiz. So if we say, if we're talking about, say, a point Z lying on X1, we need to know what Z is. And we know that this value, say Y, be the X2 dimension value of that data point. So we know Y, we need to know Z, we need to know where on this axis will that Z point lie. And these questions, whether z is less than t1 or greater than t1, whether z is less than t3 or greater than t3. So these series of questions will help us identify the location of z on x1. This is what we are trying to do. This is the whole exercise. So the location of our data point will be given by coordinates on this 2D space. So yz, if yz are the coordinates of that point that we are talking about, the new data point, and we know y, and we are trying to find out z by asking a series of questions, whether z is less than t1 or greater than t1, it's less than t3 or greater than t3, or does it lie between t1 and t3. So these questions. Now what this algorithm is doing is it is giving us these T1 and T3 values, which will help us create these subspaces or regions, and we can allocate that point into a certain region. This is what there is in that. And therefore, now we have these regions defined from the known data. We have the regions defined. This is a supervised learning algorithm. We have a supervision that we already know which questions to ask in order to pinpoint that data point on this axis, pinpoint the Z value on this axis. This is what we are doing. So now, continuing from the previous slide, this is the input space. These are the regions. These are the defining points or the value of x1. T1 and T3 are two values of x1, and similarly T2 and T4 are two values of x2. And these T1, T2, T3, and T4 are creating regions in our input space. So region R1 is defined as x1 is having value of less than T1 and x2 is having value of less than T2. When these conditions are met, we get the region R1. This is the gist of it. So if we know that a new point will come, and we know that this point is somewhere here. So now we need to identify, if we know the x2 value, which is x2 value will go like this. So this could be in R2, R3, or R5. It could be anywhere if you know the x2 value. And now we ask a series of questions related to T1 and T3 and see whether the point will lie in R2, R3, or R5. And if this point lies in, say, for example, R3, then a single value of will be given to that point, to all those points which come in this region R3. And these are the questions we are asking now. So x1, is it less than equal to T1? This one. And then if it is so, then is x2 less than equal to T2? And both these conditions are true, we get the region R1. And now if this was true and this was false, we get R2. So, so to summarize, the left part of every question we are asking is the true, and the right part will be the false one. So this will give us the regions, this will give us the defined regions R1, R2, R3, R4, and R5, through which we can allocate a new data into this input space. And by pinpointing that data in that input space, we will get our prediction, what we are trying to do through a decision tree algorithm like any other machine learning algorithm. So just like that, on the right side, we get the no's, and left side, we get the yeses. And these are the leaf nodes, R1, R2, R3, R4, and R5. These are the decisions, final decisions. These are the regions. So any data will either fall in R1, R2, R3, R4, and R5. And in case of regression, if we have numeric values, then same real valued output. So if the value is, say, is 5, for example, so every point falling in this region will be given a value of 5. This will get clearer in the upcoming example. And same goes for classification. Now, decision tree is doing this exercise, asking a series of questions and allocating region to that data point. Whether it is a regression problem, that data is a regression problem or a classification. So whether that data is numeric, like age or gender, male or female, categorical. So either it'll in both the cases we will assign it to a region. So every point falling in this region. So if you are asking about the gender, it will be male, and if you are asking about age, every data will get the value of 35 if it falls in R3 region after asking these questions. So these are the additional slides. This was an additional way of looking at how a decision tree algorithm will actually help us give us a prediction. So now coming specifically to the CART algorithm, how do we ask the right questions for splitting? So here we have our decision tree, which we got in our previous slide. These are the leaf nodes, these are the branches. So what CART algorithm will do is it will have this structure. It will have a splitting criteria, which we saw in the previous presentation also. So Gini impurity and residual reduction are two commonly used uh, metrics in CART algorithm to get that splitting criteria, to get that decision, to get these get these criteria using T1, T2, T3, and T4. So these values are obtained. What T1 will help us give a good split, and what T2 will help us give a good split, so that these regions are efficiently identified, so that these regions are helping us give us the best prediction. What T1 and T2 should be there. These are the metrics that they're giving. And in the previous, we have already seen how Gini impurity works for classification. Now we will understand how residual reduction works for regression tasks, and then how CART incorporates both of these aspects. So residual reduction technique, the metric used in residual reduction technique is variance. So how much the data points differ from the average value. We know what variance is statistically, and now we'll see how this variance is used to get that split, which we did using Gini index and information gain in the categorical data. Now, let's see an example, a simple example. So let us have these following scores and pass-fail outcomes. So these are the scores and these are the outcomes. So let one give the pass outcome 65, 70, and 75. So we don't know what is the exact score after which or at which a student can be identified as passed, and below which it can student can be said as failed. So this algorithm now will help us reach there. We have numeric data. Now we have a regression task at hand, and we have this outcome from numeric data. We need to give this prediction. So now, first we calculate the variance of the entire data set. How it is done? The mean value of mean of all these values will be 0.6, and variance, which is the difference of individual values from average value, sum of squared of those differences divided by the total number of data points will give us the variance, and which is 0.24. So now coming to the split. So what this algorithm will do is it will identify the best split. It will assess the prospective splits and then identify the best split. So for the sake of simplicity, we just take one particular split point at a data with a score of 65. So we see that intuitively 65 is where the change is happening. So let us consider splitting it at 65. Now this will give us two groups. One group will be the scores are less than equal to 65, where we have three scores, 55, 60, and 65 till here. And the second group will have 70 and 75. Now the group one will, and we will calculate the variance of this first group as in this following manner, and we'll get the variance of 0.22. Similarly, group two will have just two values, 70 and 75, and it will have a variance of 0 because both the values are on the same side, which is pass. So it will have a 0 variance. So weighted average of both these variances is calculated because we have 5 data points, 3 in the first group, 2 in the second. So it has 3/5 of the data, it has 2/5 of the data. The weight is 355 into the variance of the first group, then into the second, and we get the total variance. So if we see the total variance coming out to be 0.133. And before the split, the entire data set had a variance of 0.24. Now the variance of this data is decreasing. It is centering towards a central value. It is converging towards a central value. The variances get, so we have more homogeneous data. The data is not here and there. It is more centralized. We have homogeneous data. So it is a good split. So let us suppose that this is the best split we get, but the algorithm will actually take 65, can take 65, 65, 63, and 67 as the values for the split. So for ease of understanding, let's say out of the 63, 65, and 67, 65 is giving us the best difference in the variance. And actually the variance is actually decreasing from the total data set variance. So now let's see, now we have seen how variance reduction happens, how variance is used for regression tasks and to get that split criterion. Now we'll see how both regression and classification are done on a data set in this CART algorithm. So for classification, we use Gini impurity. Let us consider a potential split point like we did previously at study hours equal to 3. So now the study hours will decide either a final score and pass fail. So this is category and this is numeric. This is the regression task where we need to find the linkage between study and final score to get a prediction model, and study hours link to pass and fail prediction. That is the second part. So we have two side to this problem. So again, we'll get two groups. One group will be study hours less than equal to 3, and this will be the group 1, 2, 3. Pass will be 0, 0, 1. Taken. This is a subset. This is a subset from this data set. The probabilities are 1 by 3 and 2 by 3 from this. Then we get the Gini impurity. We already know the formula. We put the values, and we get the Gini impurity as 4 by 9. Then we see the second group where this is actually wrongly written, where the study hours is greater than 3, which is 4 and 5, and both of them are passing. The Gini impurity is 0 because we have homogeneous values. There is the least impure data set, and we get a weighted average of both these Gini impurities, which is 4 by 15. We have the weights here and we have the value here. So this was classification. Now we do a regression task. We are doing split basis regression using variance reduction technique. So again, we split the data into two parts. Let 3 hours be that splitting criterion. Just we are doing this just intuitively. Actually the algorithm will assess multiple values instead of just 3, and then come up with the best split criterion. We are, for the sake of understanding, we have taken 3, and we are assuming that 3 will give us the best result, just to understand how this algorithm will move forward. Again, we have the first group where study hours and final scores are there in front of each other. We calculate the variance. We have the average value. We take the difference of each of these values from the difference, and we take the sum of squares of differences divided by the number of values. We get 16.67. And then group 2. So these are the two values belonging in group 2. We get the variance, which is 6.25. Then we get a weighted average of these variance, 3 data points, 2 data points, 3/5, 2/5 of the data, the weights, and then we get 12.502 as the total variance. So let us assume now this this algorithm, there was an algorithm which would assess these values, calculate these values at different points, at 2, 3, 4, 5, and it saw that 3 is the best value at which the data is getting, we are getting a best split of data into pass and fail. For final score also, 3 give us the best variance, which is different from the actual variance of the data set. And now using these two, the cart will make the prediction. So 3 hour split was let this algorithm then found out that 3 hour split gave us the best values. So for categorical part, so this is the numerical part actually. Now we have that 3.5 hours is greater than 3 hours. So the prediction is pass, and the final score will be the mean that we calculated in previous slide. It was 72.5 if you can recall. You can skip back to that part to that slide also in this video. You can scroll back. And again, for a person who studied less than 3 hours, which is 2 hours, it is a left child. If you remember that the tree moving right and left, so it is less than 2 hours, left side of a numeric line, then he is likely to be fail, and his score is likely to be 60, which is the average score calculated for that. So now this is how CART algorithm uses both Gini impurity for classification and variance reduction for regression to build an effective decision tree model. So basically, it is assessing on both parameters, on Gini impurity and variance reduction, to get the best split. So the algorithm is supposed to work on at different values and then compare. It will give us the values where we can make an informed decision that at what point, instead of 3 it could be 3.5, it could be 2.5. In this case, let's assume that it gave us the 3 hours from both the matrix calculated, and This is how we got our prediction from the CART algorithm. So if you remember, in the very first presentation of the series, we intended to cover these 5 aspects of decision trees. Tree construction we did in the first part. We also did we also understood what information gain, entropy, gene impurity, and chi-square test, how these metrics work to give us the best splitting criterion. And today we saw how we will handle both continuous and categorical variables in decision trees. This is covered, and in the upcoming presentation on decision trees in this series, we will see how we handle missing values, how pruning is done, what hyperparameter tuning is done, and how these evaluation of these of the decision tree algorithm happens. And there are some ensemble methods, which use these decision trees as a part of it. So uh, when we have multiple trees, we have a forest. So this algorithm is called random forests. And then we'll move on from decision trees after covering these two to random forests. And then variations such as gradient boosted trees, which will combine multiple trees to improve the predicted performance and generalization of this algorithm. So thank you very much for joining, and see you in the next presentation. Thank you.